Thank you very much. I would like to thank the organizers for giving me an opportunity to talk about my work. I'm going to talk about something that so-called causal structures by first motivating them. We heard about them in Boris Dubrov's talk, and so to get a feeling about them, let's just remind ourselves two equivalent ways that we can define a Lawrencian conformal structure. So either we can define it as a class of metrics that define a line bundle in this space, so they're metrics that are proportional to each other, or we can view it as a field of cones that are the null cones of some Lawrencian metric, so cones that are strongly convex and quadratic over a manifold. So because they're cones, we can projectivize them and we get a bundle of quadrics on a manifold. So this would be so-called so if I have Rn and I prescribe a quadratic cone, that will that would exactly I'm able to recover a bilinear form, Lawrencian bilinear form, up to a scale. So I can basically define a conformal Lawrencian structure by in terms of a field of quadratic null cones, and I call this cone this subbundle sky bundle. So each fiber, which would be a null cone of our metric, would I call it the sky. Mike referred to them as celestial sphere or projectivized null cone. And this is two equivalent ways that we can define a, so I think it's not, it doesn't go forward. Oh, nice. Yeah, it's work. Yeah. So there's some incentives to go beyond the case of having a field of quadratic cones. Mainly, we can see that many interesting classes of conformal structures, they can be self-dual, Einstein-Weyl that we'll mainly focus on, or those conformal structures with shear free null congruence. They can be characterized by some integrability condition that don't necessarily require a metric. Another incentive is that in the theory of dispersionless integrable systems of order higher than 2, it seems that such structures appear naturally. Another one is to sort of this Ted Newman's null surface formulation of general relativity, in which he sort of, instead of working with a metric, he wants to work with a system of a pair of PDEs of finite type, meaning that their solution space is four-dimensional. It's an overdetermined pair of PDEs, and he sort of wants to formulate GR in that coordinate system that actually appears for us too in this three-dimensional case, but he was mainly interested in 4 dimensions. And another one is the so-called Lorentz-Finzer gravity theory that some people are interested in, and as a result, naturally, cones are deformed into non-quadratic cones. So let me just again say Finzer geometry or pseudo-Finzer geometry is, again, you can think about it as Riemannian geometry, but just threw away this quadratic restriction. So you just have a norm in each tangent space that doesn't necessarily arise from an inner product. So it can be, or alternatively, you can think of, instead of having, your set of unit vectors, unit time-like or space-like vectors, defining sort of a quadratic hypersurfaces in each tangent space. They just define some sort of non-degenerate affine hypersurface with the right second fundamental. So these are some incentives. Now we want to go beyond the setting of quadratic cones, but once we do that, the situation can be horrible. We can have the cones can have self-intersection, they can have singularity, they can have multiple connected components. So we don't want to do that. We just want to restrict to, we have a field of cones and restrict to the set of this cone bundle or this sky bundle where everything is nice and smooth. So it's pure, our treatment is completely local on this bundle, this sky bundle. So we define a local causal structure. So this term causal, this is not my choice, but it basically causality, the main ingredient is that you assign this null cone at each point. But then usually when people use causality, they consider sort of global aspects of it. But for us, it will be purely local. So for me, the crucial part is that I have these cones and I treat them locally. So a local causal structure on an n-dimensional manifold of this signature, again, the signature can be anything, but we're interested in sort of Lawrencian setting in for this talk, is given by a subbundle of projectivized tangent bundle that are called sky bundles, such that each sky corresponds to a connected, smooth, sternly convex cone in each tangent space. So they can be open also. Locally, once we have these cones in a sufficiently small neighborhood, we can sort of define this cone as a vanishing set of some Lagrangian, which is vertical in yi. So yi are vertical coordinates, and for m, we use xi's. Which this sort of Lagrangian, when you restrict it to its vanishing set, has this signature. So it necessarily degenerates because it's the vanishing set of a homogeneous function. But then the degeneracy is on the along the radii of the cone. So if you projectivize, you get a positive definite.
Clarification. So in a strongly convex, do you include like a single line or a half plane, or those are excluded as called?
No. Yeah. So I want things to define a strongly convex cone. So I do not consider like a hyperplane as a cone. No. What? No. Yeah, it's good. It has to be at least. Yeah, it's a cone. I could mention one cone. Yes.
So if you, for example, consider cubic, right, structure, then there will be parts where your theory is applicable because it's pseudo-convex, and necessary will be parts to which it's not applicable.
Yeah. So we have, if you have a cubic, then you have to sort of cut it into parts that this Hessian has the same signature, but then sometimes you could degenerate, so you have to cut those and treat those that has again a different signature, has to sort of stick to the sort of single connected component when you're sort of doing this partitioning of the cone in each tangent.
But you just restrict to pseudo-convex, right? So if the signature is
right now, yes,
you can.
Yeah. But it can easily be done when the signature changes to PQ. For this, because later we'll go to 3D and only Lawrencian signature makes sense in 3. So if you multiply your Lagrangian by, let's say, another function that is defined and homogeneous on the tangent bundle, you can get the same cones. So this is sort of some sort of ambiguity in the defining function. But if you're interested in some sort of coordinates, this is one way of putting coordinates on your sky bundle. So we say two causal structures are locally equivalent at these 2 points if there's a diffeomorphism from an open set of this manifold to another one, so that when you restrict the cones to that open set, the naturally induced map, the push forward on the projectivized tangent bundle, sends one cone on this one to the cone on the other one. So it's like if these cones arise from metrics, Lorentzian metrics, then this condition means that the metric here is sent to a multiple of the other one. This would be conformal equivalence here. So how do we compute? We don't have a metric, nothing. So what do we do here? Well, one thing we have, if you start, let's say, with this local defining function L, you can cook up this one form that I call a projective Hilbert form. So what's the interpretation of this one form? First of all, remember that this Hessian has to have maximal rank. And when this has maximal rank, it turns out that this one form on our sky bundle defines a quasi-contact structure What does it mean? So here we have, this is odd dimensional projective tangent model. The sky bundle is always even dimensional. And the quasi-contact is a maximally non-integrable one form, meaning that it satisfies these conditions on this sky bundle. And the interpretation is that, so at each tangent space, you have this cone. And let's say take this ray. It corresponds to a point upstairs on the sky bundle, right? When I put a hat, it means that I'm considering the cone instead of its projectivization. So this is a cone in this tangent space, and this ray corresponds to a point on the sky bundle. And consider the affine tangent space to this cone along this ray, right? Now, take the, okay, I'm gonna define this, just keep that in mind. So here, immediately we see on the sky bundle, we have, first of all, take the pre-image because we have a projection from sky to M. So take the pre-image of 0, it'll give you the sort of a vertical distribution of the fibration of the sky bundle over M. And then take the pre-image of this ray, right? So this would define another distribution on the sky bundle, and which is one, the rank of this is one more than this vertical distribution. Also, we can take the pre-image of this hyperplane along each ray. So this at each point, when they take the pre-image of this affine tangent plane to the cone along this ray, this would again lifts and gives me a co-rank 1 distribution at each point of my sky bundle. So this, if you remember Boris-Dubrov's talks, is a filtration on the tangent bundle of the sky bundle. And this Hilbert form is simply the annihilator of this co-rank 1 distribution. Right? It defines a quasi-contact distribution. So now this is a filtered manifold, and we can do computations if you want in local coordinates or abstractly. And it turns out because you have a quasi-contact structure, there's a degenerate direction. Let's call it L, means that L is annihilated by omega and its exterior derivative. So you can actually explicitly say what it looks like. It's like it's spanned by this vector field. And then it turns out that this distribution here, it has a splitting, meaning an integrable subdistribution of co-rank 1 and a line field, and it's a splitting. And note that if L is quadratic, meaning that it arises from a Lawrencian metric, so if these are constant at each point of the manifold, then this guy is exactly the null geodesic spray of a Lawrencian metric. So this way, we basically have a filtered structure. We know that this T-1, this distribution is a splitting, and we can basically solve the local equivalence problem for causal structures. So that means how do we sort of distinguish geometric structures? I'm gonna make a list here for people to just, again, if you remember in this talk, to just remind ourselves of some of the examples that we saw previously. So remember in Lawrencian geometry, let's say we want our flat model to be the Minkowski space. We have a Cartan geometry of this type, as we saw, and we have the notion to do the computations. We have the Levi-Civita connection, and the fundamental invariant, whose vanishing implies that the space is locally Minkowski, is called the Riemann curvature. Also, we saw conformal Lawrencian geometry. Again, it's a conformal geometry of this type. This is the first parabolic on an n-dimensional manifold. And again, in there, we have normal conformal connection that you can use to do computations, particular tractor calculus. We can consider the tractor bundle and the connection induced on it. Then the fundamental invariance is the Weyl curvature, and its vanishing implies that the space is locally conformal to the Minkowski space. Another sort of geometric structure that's sort of interesting for us is this Lawrencian Finzer structure. So remember, the way to think about Lawrencian structure is that you just have a think about Lawrencian metric, but then you have the unit space-like and unit time-like vectors, the set of unit space-like and unit time-like at each tangent space, and you just allow it to be deformed to an arbitrary affine hypersurface with the condition that the sort of second fundamental form keeps the same signature. So in that case, you again have a Cartan geometry, but of this type, which is different from here. So if you want to deform the set of, let's say, space-like vectors, unit space-like vectors, then you're in this Cartan geometry. And if you want to deform your time-like vectors to something affine hypersurface, it's of this type. And then in there you have, it's a Cartan geometry, you have many, actually people came up with different notions of connection, in particular Cartan, Chern, Berwald. And there are again now two fundamental invariants under the name of flat curvature, and the other one is Cartan torsion. And its vanishing implies that you're basically, you're dealing with locally Minkowski space. So another one is that, for instance, is Cartan is 0, then you're in the realm of Lawrencian geometry. So you go down, you can descend to a Lawrencian geometry. So in causal, this is just sort of by the identification I did previously, one can immediately, when that filtration is, you recognize that filtration I described, and then you do follow this Cartan treatment, you realize that you're dealing with a parabolic geometry of this type. So this is the parabolic subgroup which preserves a null line and a null plane. So this, your causal structures are of this type in dimension 4. It's just you have to mod out by Borel. And again, in there, this is a parabolic geometry, and you have this sort of nice regular normal Cartan connection that arises from this for all parabolic geometries, in particular this one. And the fundamental invariants are, this is just a name inspired by Finzer geometry, Weyl flat curvature, and Fubini cubic form. So if they are 0, then you know your causal structure is basically the sky bundle of Minkowski space locally. If Fubini is 0, then that implies your skies are quadrics, and you're dealing basically, you're in this setting, Lawrencian geometry, conformal Lawrencian. So now that we have an idea what these causal structures is, let's see some examples. So the nicest example for conformal Lawrencian geometry in dimension 3, let's say, you can do it in any dimension, is the flat model. And it has 10-dimensional symmetry group. So if you want to, let's say, consider some causal analogs of this, let's say a defining function is given by this for some exponent p. So if this p is equal to 2, then again, you're dealing with Minkowski. But if you allow it to be anything other than these numbers, then this defines a causal structure that is actually a sky bundle is not homogeneous, and it has 4-dimensional symmetry group. But this is not sort of the best, sort of most symmetric causal structure you can get that is not conformal. It turns out that the submaximal, meaning like non-flat but with highest symmetry, has 5-dimensional symmetry group, and the cones, these skies, are given by homogeneous curves that were actually, there's this work of Dubrov and Konrakov where they sort of give you what curves, because your skies are now going to be projective curves inside P2. So they know what are the homogeneous curves, and you can cook up what are the defining functions for such causal structures, and they're of this form. And they have 5-dimensional symmetry group. And there's another example that actually was hard to write. It's kind of weird. So now that we have an idea about causal structures, for instance, in dimension 3, one can wonder what are some, what we can do with it? What are some analogs of some interesting classes of conformal structures that we know? So for instance, I want to do like dimension by dimension if you want to go. So the easiest dimension probably is dimension 3. And in dimension 3, we have this interesting classes, structures that are sort of conformally invariant somehow, that are called Einstein-Weyl. So Weyl structures is defined by, you have a conformal class of metrics, Lawrencian, and a torsion-free affine connection, such that the affine connection preserves the conformal class. So this phi is some one form. So you can think about this as the pair G and phi, sort of defining an equivalence class under this relation. So if you change your G conformally, then phi changes this way. So you can either define a Weyl structure this way or by this sort of equivalence class of metric and a one form. Or if more physically, you can think about it as Weyl structures is a compatible pair of a conformal structure and a projective structure. So a projective structure is a set of torsion-free, let's say, affine connections, which share the same geodesics as unparameterized curves that we've seen in a few talks. And we just require that if there is a choice of affine connection in this such that the light-like geodesics of G are autoparallel with respect to that connection. So this defines, again, another way of defining what a Weyl structure is. So we call a Weyl structure Einstein-Weyl if now, because we have a torsion-free affine connection, we have the Riemann tensor and we can cook up the Ricci tensor of this affine connection, which is not necessarily symmetric. So we take the symmetric part of it and we require that it's proportional to this, an element in this conformal class for some factor lambda that doesn't have to be constant. So for instance, one can show that if this one form is closed, then locally a conformal, this conformal class is Einstein-Weyl, implies that locally there is a Einstein representative in the conformal class. But Einstein sort of metrics in dimension 3 are not so interesting because they're just, they have constant sectional curvature. But this is like an, sort of non-trivial generalization of Einstein condition in dimension 3. For instance, you can see that S1 cross S2 or S1 cross S3, it can be shown that they're not Einstein, but they are. It's not too hard to show that, but they are Einstein-Weyl with the just a little bit of work. Moreover, if you're in the setting of 4-dimensional metrics of plus plus minus minus signature, and if you impose self-duality and require that the conformal class has a conformal killing field, then also they result in if you reduce by this conformal killing field, then on the downstairs you get an Einstein-Weyl structure. So this is just some motivation why these structures are interesting. So this is some comment that Xavier made during Boris's talk, that he was talking about this filtration. And then one can ask, okay, this is like generically geometric structure is like can be described this way, but some interesting classes are obtained when you sort of require some integrability, some subdistribution is completely integrable in that filtration. And this is sort of, for me, is the content of many of these tutorial characterization of these interesting classes of geometries. For instance, for Einstein-Weyl, there's this work of Hitchin that also is attributed to Cartan, but I couldn't quite find it in his work, is that Einstein-Weyl property for a Weyl structure is equivalent to having on your manifold a 2-parameter family of null surfaces, so they're null with respect to the conformal structure, and also totally geodesic with respect to the projective structure. So once, if your Weyl structure satisfies this sort of integrability condition, then you know it's Einstein-Weyl, and vice versa, it's equivalent. So here, just null means that the annihilated or each tangent plane of these surfaces is null. And this 2-parameter family of null surfaces means that at each point of the manifold and along each null plane, in your tangent space, there passes a unique null surface, right? This two-parameter family has to satisfy this property. So it turns out that once you have this property, then, so at each point of the manifold, there passes a one-parameter family of surfaces, takes the sort of tangent place to those surfaces, and they envelop a cone, and that cone would be exactly your sky, the cone over your sky. So the objective of the rest of this talk would be to sort of consider causal structures and augment it with such integrability condition and see what we get. So again, this two-historial characterization that Hitchin gave was inspired by Penrose's two-historial characterization of self-duality. So it's four-dimensional metric in 4D is self-dual if, again, there's a three-parameter family of null surfaces. So this causal structures were sort of in dimension 3 were special, and they were studied by others. And that was basically the whole motivation why I worked on them, is that they realized, but people were coming at it from a different angle in the way I'm going to say. So it turns out that this was the work of Sparling and Holland, that three-dimensional causal structure, they correspond to third-order ODEs under contact transformation. So third-order, you just take any third-order ODE. F can be anything, okay? Away from nasty points of F. Let's say you have existence theorem, and then consider contact transformation, meaning that take away all the coordinate dependence of this ODE. So allow these transformations, right? And with such that this at the end becomes the derivative of this and this. So this adds another constraint. But basically contact transformations are transformations of this type. And they cooked up a Lagrangian on the solution space. So the solution space of this is three-dimensional, locally defined if you have existence theorem, because the solution of a third-order ODE is defined by three constants. So you have a three-dimensional space, and they cook up a Lagrangian, sort of cooked up implicitly from this ODE. And they showed that this Lagrangian, defines cones, and these cones define this causal structures. So again, let me just say what, this is what I said previously. Here, the sky bundle is four-dimensional. So you're on a three-dimensional manifold, and each sky, because we're projectivizing, defines a curve, a projective curve in P2, right? And then the sort of this distribution, T-1, in this case, will have rank 2. Remember, it's just the pullback of this array to this four-dimensional manifold. So the fibers are curves. These are one-dimensional fibers. So this is the rank 2 distribution. And as we showed previously, it splits into two line bundles. So as soon as you see, so this rank 2 distribution, it has growth 2, 3, 4. So if you take the Lie bracket of it with itself, it has rank 3, and then another Lie bracket gives you the entire tangent bundle. These are called angle structures. And that's why people like these distributions. And that's how people such as Chern all the way to Sparling and Holland considered local equivalence of third-order ODEs. And they realized it exactly defines geometry of the type that I described previously for causal structures in dimension 3. And there are two weighted scalars as the fundamental invariants. So this usually goes, let's call I0 the Wunschmann invariant. And this would be what in conformal geometry would be a Cartan tensor. But this is a generalization. So if this sort of is 0, then you're in the realm of conformal geometry, and this corresponds to a component in the Cartan tensor. So if you push it down, go to the three-dimensional manifold, so push down from this 4, your sky bundle, to 3, this generates the entire Cartan tensor. So again, if you like coordinate computations, you can view this sky bundle. If you go to affine coordinates, you can basically describe your projective curves as a function of, depending on your base, x1, x2, x3, and then t is your sky parameter. and then find these invariants, y0 and this Wunschmann invariant. So for instance, in this coordinate system, if you have this looking at it from a sort of field of null cones, this is sort of an expression for this invariant. So it depends on the fifth jet of H. And if you're looking at it from an ODE point of view that I described previously, this would be the form in terms of where this is the ODE function. And this invariant is sort of way more interesting because if you're looking at it as, if you define your structure in terms of ODE, it just has one term, the fourth derivative of f with respect to f y double prime. And if you're looking at it in this coordinate system, it's just much nastier. So this coordinate system can make some things easier, some things more difficult. So I call a causal structure augmented if it's equipped with a two-parameter family of null surfaces. It's the most obvious generalization. But I want to interpret it this way, that C, the sky bundle, is foliated by surfaces that are projected to surfaces downstairs, and their tangent plane lies in this affine tangent space to the cone. So I want my sky bundle being foliated by surfaces such that they again, exactly projected to surfaces on M, which are in this sort of generalized setting of cones, exactly the tangent bundle sort of lies in here. So now this is the integrability condition that we imposed. First of all, we again have the filtration we defined previously. So we have this rank 2 distribution, which we said splits into two line bundles. But then because of this augmentation, the second filtration, the second part, would have a splitting into the vertical. Remember, it has to have rank 3, right? But then there's a splitting into the vertical and a rank 2 distribution that is integrable. And its integral curve gives you this sort of augmented surfaces, this foliation by surfaces. So once now you want to define the local equivalence of augmented causal structures. So not only you want cones to be mapped to each other, you want also these surfaces to be mapped to each other. And it turns out as a Cartan geometry, if you look at it, then your Cartan geometry, the bundle is reduced 3 dimensions because you required this splitting. There's a 3-dimensional reduction. And so this is a theorem that sort of equivalence of these augmented causal structures that I'll say why I attributed to Cartan and Notoriously. So they augmented causal structures define geometries of this type. Now, this is the same, this is the principal bundle we had previously that had 10 dimensions for conformal structures, but it's reduced by 3 parameters. And it's of this type now. R3 semi-direct product CO21 and B is upper triangular matrices in CO21. Now there are 4 fundamental invariants. You have this Wunschmann, and this sort of generalized Cartan goes away because you've reduced that part of your structure, and you have actually 3 more scalars. So the vanishing of this 3 means that you're dealing with a flat model. So the reason that I said this sort of theorem was known before is that it turns out, if you look at it carefully, augmented causal structures are in one-to-one correspondent with now point equivalence classes of third-order ODEs. Before I said causal structures, they're contact equivalence classes. So you have an ODE and allow contact transformation, you get 3D-dimensional causal. But now you allow a sort of smaller group of transformations. So this point equivalence is that you don't change y prime. It's so you have transformations that are of this type. X goes to X, which is X and Y, and then Y is you allow transformations to be of this form, something of X and Y. So and everything else for Y prime, Y double prime, they're prolongations of transformations like this. You don't have, like contact transformation, don't allow y prime to appear in your transformation. And this actually is not so difficult to see the relation between third order ODEs and this augmented causal structures, because, so remember that we defined, we had a 2-parameter family of surfaces. So you can view it as, let's say, fixed T, and then the surface would be 2-parameter family of surfaces can be described as, let's say, I'm trying to heuristically viewing it. So you have 2-parameter family of surfaces. You can think about it as a 1-parameter family of foliations. So if you fix T, for each value of Y, you get a level set, right? So this gives you a foliation, and you vary T, and you get a 1-parameter family of foliations. That would sort of gives you having a 2-parameter family of surfaces, but then by consecutive differentiations, you can, let's say you have Y, you have U prime, U double prime, and you use those to eliminate X1, X2, X3, and then you differentiate another time, you have U triple prime as a function of Y, U prime, U double prime, and T. So this is how you recover, you sort of heuristically, a third order ODE. Now, so far, it seems like everything has been going tautologically. There's nothing really surprising. But remember, in Weyl structure, we had this conformal geometry and sort of this projective geometry. So we had these geodesics as unparameterized curves, and we have the conformal class of a Lawrencian metric. So we don't see something resembling projective structure here so far. Because the reason is, in general, we don't have a projective structure. We have to think of a larger class of structures that is referred to as path geometry. So projective structures are special classes of path geometries. So path geometry, roughly speaking, is sort of a generalization of projective structure, meaning that you have a manifold, 3-dimensional manifold. Through each point and along each direction, there passes a unique curve. We call it a path geometry. Locally, this is how the way of viewing it. And again, you can cook up a Cartan geometry for these. They're of this type, right? This is the parabolic that preserves a line and a plane, and in parabolic in SL4. And then now they have the fundamental invariance. This is this Cartan geometry is in fact parabolic geometry. As the fundamental invariance, they are you can view it as a torsion and a curvature. So this is a torsion and this is a curvature. So for instance, again, you have this duality that if, so you have this, you have this sigma, let's call it sigma, a 5-dimensional manifold, and as viewing it as a projectivized tangent bundle of some M3, maybe locally. So you have two invariants here. You have T and you have S. They're weighted, so they're defined up to this. And let's say if S is equal to 0, then here your structure descends to a projective structure on M, on the 3-dimensional manifold. And if T is equal to 0, then you descend to a space of paths, which is 4-dimensional. And here this has a conformal geometry that is self-dual. And this guy can be thought of as the self-dual part of, depending on how you want to define, self-dual Weyl curvature of this conformal structure of signature 2,2. So this in particular, this is a quartic, because remember the self-dual and anti-self-dual Weyl curvature in dimension 4 as a GL2 module can be thought of as a quartic. And here we're assuming this would correspond to, this is actually a quartic binary, the same way that the self-dual Weyl curvature of a conformal structure in dimension 3 is a self-dual, is a binary quartic. So the curvature is a binary quartic, and this torsion is a binary quadric. But the interesting fact, now this is the first sort of non-trivial observation, is that this quartic this curvature, has a root of multiplicity 3. So it's not generic. So there's something special about path geometries that are obtained from this augmented causal structures. So if you remember, we had 4 fundamental invariants. We referred to them as I0, S0, R0, and C0. So if, for instance, 2 of them vanish, this I0 and this Wunschment, and this is called Cartan invariant, then the path geometry is projective. And in fact, this is necessary and sufficient condition to have a Lawrencian Einstein-Weyl structure that I defined previously. Otherwise, you have something more general. But this general is, again, sort of not that surprising, because remember, we augmented it with these surfaces, and these surfaces are, quote unquote, totally geodesic for this path geometry. So if a path starts from on one of these surfaces, it remains on it. It's not so hard to define a notion of totally geodesic in path geometry. Once you have these definitions of Cartan geometries, it's easy to sort of cook up the right notion of what it means to be totally geodesic for path geometry. And furthermore, so you have these paths on these surfaces, and they define a projective structure on the surface. So this is really similar to the Hitchens characterization of this Einstein-Weyl. We have something extremely similar, but everything is just another more general Cartan geometries, path, causal, and these things. But this is not, I mean, this is kind of tautological. There's nothing sort of seems to be interesting. So we want to consider more interesting structures out of this. So to do this, we have to again go even, define even more exotic Cartan geometry. So it's like my talk is basically a zoo of Cartan geometry, sort of a. So in this, we're going to define the so-called Finzer-Weyl structure. So again, as I said before, you have to think of Finzer as sort of having your bundle of time-like or space-like vectors, right? Because which are defined like a quadratic hypersurface, and just deform it to something that again has non-degenerate second fundamental form. So this is what I mean by tangentially non-degenerate. But if you want, because again, it's useful for us to think about Finzer geometry abstractly. As I said, deforming things, it's not so satisfactory and not precise. So if we want to, for causal geometries, we did that. We had that filtration, and any manifold with that filtration defines a causal structure and is a sky bundle over a manifold. But for Finzer, this again can be done. So for Finzer, you have to work on these, again, these bundles of unit time-like vectors or space-like vectors. It turns out that you have to define it as a manifold, let's say in dimension 3, as a 5-dimensional manifold, which is contact and has a distinguished contact form. So, and it has a Legendrian foliation, and the foliation is equipped with a bilinear form. So this bilinear form, in case, so this, let me just give you a perspective. So here we have, let's say this is our 3-dimensional manifold, and we have, let's say, the bundle of space-like vectors defines, let's say, a hyperboloid at each point. Right? So the whole idea of this definition is that this is a 5-dimensional manifold, right? It's fibered over a 3-dimensional manifold, and these fibers, these are surfaces, right? Affine surface. These are 2-dimensional fibers, and they are Legendrian with respect to a distinguished contact form. First of all, this manifold has a contact distribution, and the contact distribution, it's not too, again, not too hard to define. If, let's say, these things are given by your defining function f equal to 1, let's say, in the case of Riemannian case, it will be Gij yi, yj equal to 1, let's say. So this is f2 squared. Then this contact form would be gij yi dxj. So this is alpha. So this would be, you have to restrict it to the case, to the set of f equal to 1, to this set of unit space-like vectors. Right? So this defines a contact distribution. In fact, it's a distinguished contact form for you. And these surfaces define a Legendrian foliation, and there's a bilinear form on each of these things. So the reduced orthogonal group has to be compatible with the Levy bracket in this contact distribution. So now you can, so this is a Finzer. And now we want to sort of define its notion of Finzer-Weyl structure, which is, if you remember the Weyl structure, now we can sort of, this was in a paper by 2 Japanese mathematicians, but it's not too hard to mimic the definition of a Weyl structure in the Finzerian setting. So you have, you can think about it as having this distinguished contact form. So you don't have a metric anymore, but you always have this contact form, distinguished contact form. So this would play the role of the metric in Finzer geometry. And you allow it to scale. Right? You consider the conformal class of this. And on this bundle, on this 5-dimensional bundle, you sort of want a connection, and I'm not going to give the details because it will be too much, but maybe not that interesting. This connection would be, if you know path geometry is a parabolic geometry, arises as some sort of Weyl connection for the path geometry on this 5-dimensional space. I'm not going to say how I cook up this connection, but you can view it as a sort of a certain connection and a conformal class of a 1 form, such that the connection preserves the conformal class of the 1 form. And we allow only conformal scaling that are in terms of sort of scale it. So x, remember, is coordinate on the base, and y are coordinates of the fiber in the tangent bundle. So we only allow this scaling. So sort of we at each point, we only allow a homothency. And if you fix x, we just scale this hyperboloid bundle, or this bundle of space-like vectors. So you can equivalently define it as equivalent classes of your Hilbert 1 form and another 1 form, so that under this relation, and this defines the so-called Finzer-Weyl structure. So once you have this definition that is not too hard to cook up, you can solve the equivalence problem and then see that, you know, there again, they define Cartan geometries of this type, and the fundamental invariants are given by a symmetric cubic, a bilinear form, and a 2 form. So if this 2 form is 0, for instance, then you know you're working with a Finzer structure up to homothency. So now that, but remember, we wanted to sort of relate it to this augmented causal structures. And so I just, in order to make that link, I just need to review some very well-known facts about, old school projective geometry of surfaces. That, so these, remember, this is the set of space-like vectors, right? We're deforming these hyperboloids into some other affine surface. So if this is 0, that cubic is 0, then these surfaces, they are hyperboloid, and we descend to, we're in the realm of Lawrencian metrics, and this would be space-like, unit space-like vectors. If we sort of make this scalar, this invariant, Remember, this was the bilinear form, which has to do with the second fundamental form of these surfaces. If we cook up this invariant, it's called peak invariant, and if it's 0, and remember, always because we're dealing with space-like vectors, unit space-like vectors, this surface has indefinite fundamental form. Then that means these surfaces that I have here, these surfaces are ruled. If I form this combination, this is known as the Chebyshev form, and if this is 0, then I know these surfaces are so-called proper affine surfaces. So, proper affine spheres. So affine, in the study of hypersurfaces, affine hypersurfaces, there are these hypersurfaces that, when you want to study them, you have to cook up a frame at each point of the surface, like a Frenet frame in the case of curves. Now you cook up this frame, and there's always a transversal a vector in your frame, and you can ask when these transversal vectors, that always there's a distinguished transversal vector at each point, when do they intersect for all points at one single point, like a sphere? So a sphere, if you take the normal, but you have a metric for spheres in Euclidean space, then the normals intersect at one point. But when you want to study surfaces under, let's say, action of general linear group, there is no metric. Right? You want to say when they are equivalent under the action of general linear group. But again, you can cook up this frame and ask when this sort of well-defined notion of transversal vector at each point of the hypersurface intersect at one point. And you call them affine spheres, those surfaces. So if this quantity is 0, then you know that these surfaces are proper affine spheres, meaning that that center is inside the it's a point that is not an infinity. It's an actual point, not at infinity. So you know that this is 0. These are proper affine surfaces, and that center is the origin at each tangent space. So, for instance, if proper affine spheres that are ruled, they're exactly can be described this way. There's a function ax that satisfies this equation. So to make sense of these augmented causal structures, I have to define notion of integrability for Finzer-Weyl structures. When do we call it integrable? This is almost like, notion of Einstein-Weyl, but for this, I want to cook up something like similar to Einstein-Weyl, but for this class of Finzer-Weyl structures. I call them integrable if there's if each of the set of unit space-like vectors, sigma x, is a ruled surface, right? And so each of these things is a ruled surface, not necessarily a hyperboloid. And the bundle, the 5-dimensional bundle, is equipped with a 2-parameter family of 3 manifolds, such that they are projected to surfaces on M, and they are null with respect to certain non-degenerate bilinear form on sigma. So sigma, always here, you have a degenerate bilinear form, which is given by the osculating quadric of these surfaces. So for instance, if these are all hyperboloids, then that osculating quadric for all of them is the same, and then you get it sort of descends downstairs. But in general, you just have a degenerate bilinear form up there that does not descend downstairs. So you have that degenerate bilinear form for free, and you require that these 3 manifolds are null with respect to that. And moreover, if you intersect it with this sort of ruled surfaces, you want that intersection, which necessarily is a curve, you want that curve to be a ruling line of this sort of set of unit space-like vectors. So this is sort of a little bit, maybe, if you see the geometric picture, then it makes sense. Otherwise, just a notion of integrability for Finzer-Weyl structures. But then it turns out that integrable Finzer-Weyl structures, for which this unit space-like vectors are ruled affine spheres, they're in one-to-one correspondence with third-order ODEs with vanishing Cartan invariant. So this is 0. So this is some sort of integrability condition that we can identify with these class of third-order ODEs. And their generality is given by 4 functions of 3 variables. I think I have 5 more minutes or 3. Okay. Yeah, I'm almost done. All right. Now, this is integrable Finzer-Weyl. We want to cook up something like Einstein-Weyl. So now, remember that we always had this path geometry defined for any augmented causal structures. So now we require that this is 0, right? So because we have now this torsion, a binary quadric, and this one a binary quartic, naturally, we can require this condition be satisfied, that this torsion is the conformal class of this torsion. You can easily write, instead of writing it this way, you can write it like T equal to some, for some, is proportional to the metric for some proportional, for some function lambda. But this remember, this G is cooked up from some, this degenerate quadric that I said previously, that sort of arises as the osculating quadric of each of these space-like unit vectors. So I can, in natural condition, immediately, if you know how these binary quadrics look like, is to require that they define the same conformal, the conformal class are the same. And that's why you require this. Then, with quite a bit of more computations, tedious but straightforward, you see that the set of such, I call them Finzer-Einstein-Weyl structures, splits into either Einstein-Weyl, which is known before, this invariant vanishes, so these are Wunschmann and Cartan are 0, or what's known as a Finzer-Weyl structures of constant flat curvature. And for these guys, the torsion of this path geometry is 0. For these guys, the curvature is 0. For these guys, the torsion is 0. And then a nice consequence of, so this is too complicated to describe, but then if you go to the space of paths, so just like this double fibration I described here, things become much more clear that, because we had a path geometry here on the 3-dimensional manifold. So you go to the 4-dimensional space of paths, which Hitchin calls that mini-twistor space. These mini-twistor space, they have a half-flat Kähler structure. So by epsilon, if it's -1, it's usual Kähler. If it's 1, it's para-Kähler. If it's 0, it's null Kähler. So because we're familiar with Kähler, let's forget about this epsilon and call it Kähler. So depending on the sign of this flat curvature, if it's positive, then you get a half-flat Kähler metric whose Weyl curvature has type 3, has a root of multiplicity 3, and its Ricci curvature defines a Kähler-Einstein metric. Sort of so a natural name for these metrics would be Ricci-Einstein-Kähler metrics, which is kind of weird. So there's Einstein to the 2nd order. The Ricci curvature defines an Einstein metric. And you can find their local generality is given by 3 functions of 2 variables. And the final result is that, so I did it only in the case of para-Kähler in this slide, but I'm not going to continue that. This actually all. So if you start with, let's say this is para-Kähler case, but in the Kähler it's the same. If you require that you start with a para-Kähler, in this case, geometry, and you require that this Ricci takes this form, so there's a co-frame reduction for Ricci. This is an invariant condition. So in this case, the structure group is reduced to the Cartan subgroup, and you require that Ricci takes this form. Then, and you require that the sort of repeated root of the Weyl structure is given by this null 2 plane. then you can show that the Ricci tensor defines a paracalar Einstein metric of type 2, and all such sort of structures arise from integrable Finzer-Einstein-Weyl structures. That's sort of the main point, and it's so easy that you can integrate everything. So it's actually solvable. So you can find by looking at the structure equations, you can see this 3 functions of 2 variables. Actually, you can explicitly find a coframe by using Darboux coordinates. You can find such metrics explicitly, and for some functions u, v, w in terms of T1 and T3, and T1 and T3 is a sort of this 4-dimensional manifold fibers over a holomorphic or paraholomorphic curve in this case. And even you can find explicitly what are the 3rd order ODEs that correspond to these classes of geometries. So I think I'm going to stop and just go to the sort of directions, and thank you for your attention.
Thank you. Questions? We have a very elementary question. At the very beginning, you explained the Cartan geometry for these causal structures. There was this P12.
So P12 is the parabolic. So in conformal geometry, it's P1 is the parabolic subgroup that preserves a null line. P12 is the parabolic subgroup that preserves a flag of a null line inside a null plane.
And the coset space, corresponding coset space?
So the coset space, so if you go to, let's say, SON2 mod out by P12, this would be, you can view it as locally as exactly the sky bundle of the Minkowski space. It's, or the quadric, if you
Yeah, okay. Yeah.
Yeah. Yeah, R1 is too complicated to write down, so I didn't write it down. But then I can give it to Maple, and it solves and gives me exactly the 3 cases that I have. So the 3 cases where I told you I have this epsilon scalar. So epsilon can be -1 for scalar, +1 for paracalar, and 0 for null scalar. And it exactly gives me, generates ODEs that functions F that satisfies these PDEs and have these, one for when this is 0 and one it's non-zero. One has to check. I mean, I don't trust Maple, but I have my own coordinates. But